So this work is entirely focused on full page recognition. So the way it was conceived, it was by analyzing how optical music recognition works. For full page transcription, we usually rely on pipelines for that. And those pipelines are based on performing layout analysis on the music score pages for extracting all of the music staves that are relevant to transcribe, and then use a single staff transcription system that retrieve the content of each stave or of each staff, and then concatenate their content to get the final transcription representation of the page. So although end-to-end OMR is defined as such, it is not entirely end-to-end because we need several steps with usually human feedback to perform the transcription. And this led to some problems. The first one is that the research field has focused only on monophonic documents, and there are some all of the other documents that are left behind. For example, the ones that contain lyrics and others such as Pianoform music scores, because their formulation of full page OMR didn't match the problem of transcribing these scores. Although I have to say that there has been some recent research that focuses on these cases. For example, some previous works that we've done were based on rotations and unfolding for performing this on this kind of documents, although we couldn't get free of the layout analysis step. And it was indeed an ad hoc solution that reduced the problem to monophonic transcription, but just making it compatible to other documents. This has a lot of problems. For example, it is encoding dependent. It depended on the hand-kern notation solely. It is hard to scale to many voices being interpreted into the same music score. And in general, it is impracticable in full page without a layout analysis step. So we needed to search for a full end-to-end method, which was able to transcribe beyond monophony, which was able to transcribe full pages with more music testers than monophony. In this case, we indeed focus on transcribing Pianoform scores because they are the most difficult ones, both in image transcription and in language. So what is the sheet music transformer? Well, the sheet music transformer, it is a autoregressive neural network where you receive from the input of a full page score and goes down from a feature extractor process, usually a convolutional neural network. And the representation of that, it is added to a 2D positional encoding to have a representation of the position both in the X and the Y axis. This is very relevant. And we get some context out of that, which is a feature map. This is fed into 8 transformer decoder layers, the transformer decoder we already know from machine translation, with a cross-attention mechanism that receives that input context from the feature map. Then the model, it is fed with the previous prediction. It has an autoregressive behavior. So we first start with a start of sequence token. We do it through an embedding and a 1D positional encoding. And the outputs are projected into the notation projection vocabulary, and we get a prediction, which is feedback into the input of the transformer, and the model starts transcribing the music score until an end of transcription token is reached. So we end the transcription process. So this is the basic working of the sheet music transformer. The output format in this paper, it is hand-kern. So the ground truth we usually do, and the output is in hand-kern notation. I have an example here on the right. But the problem is that sometimes hand-kern, it is very complex. It has a lot of notation particularities that makes the vocabulary too big. So in these experiments specifically, we converted to the basic extended kern, which was presented in other research. What it does is to constrain and canonize the hand-kern notation, and also it divides it by the most elemental semantic information of the music score. And the most important fact is that it reduces the 20 or more than 20,000 symbols of vocabulary hand-kern produces to just 188 unique symbols, which is a heavy improvement for compactness and also for performing transcription. So there is one thing also that when transcribing full page scores of monophonic, or in this case on Pianoform scores, We cannot do it straight away into the sheet music transformer and autoregressive mechanisms because there is something concerning that there is a considerable gap between reading a pianoform system, what the state of the art does, and pages, which is the reading order interpretation. First of all, music system, it is read from down to up and left to right, as I show here. So there is one reading order hierarchy. But in this case, we have to go from down to up and also left to right. And when we end a system, we have to jump to the next system and continue reading on that order. So in this case, we have one reading order hierarchy, which is from down to up and left to right. And then the other one is that we have that sub hierarchy with another more hierarchy, which is jumping between systems. So this has to be taught somehow to the model. The way we approach this is through a curriculum learning. In this case, we have first system level pre-training with synthetic data. So we generate synthetic images with the Grandstaff data set, which is a synthetic corpus we have on the system level. So the model learns how to read that first reading order hierarchy. Then we do an incremental reading order learning. So in this case, what we do is to produce pages from that synthetic data. And we start increasing, like over time, the number of music systems that have to be transcribed to just make a more complex case. And finally, we do some fine tuning with curriculum learning in this case, because the data sets that we are working with also have very few data. So the transition between synthetic data and real data has to be smooth. So in this case, we perform a third curriculum learning stage where we fine tune into the actual data set we want to transcribe. And we leave a 20% of synthetic samples to avoid overfitting to the training data that can happen in these such scenarios. So the synthetic generation, it is very straightforward. We have a 100 kernel system spool, which is the Grandstaff dataset, and we perform random sampling through them. We sample many 100 kernel systems, and we join them through an automatic algorithm. So we produce a single 100 kernel file. This is rendered with Verovio, and then we perform some post-processing to add some realism to the images, such as textures, title, authors, some distortions. So we have three cases of synthetic generation. This is the basic one without post-processing. This is with some textures applied with it. And this would be like the full page that we usually feed the sheet music transformer with the textures, authors, and also some distortions on the margins to just make more data variety out of it. So the experimental setup that I am presenting today, it is the one with the real datasets, scanned datasets in this case. We have first the Mozarteum dataset, which is 101 samples of Pianoform scores from the Mozart Digital Museum. We extracted from it, and they are encoded in the beacon notation. We did some conversion from AMI to that. And then we have the Polish digital scores, which were lent to us to work with, which are 117 samples with rather an average page size, which is big. And they are encoded natively in Handran kern, so the conversion to beacon was very straightforward to our tools. As I said, the research also covers some other datasets, but we focus in this case to real datasets, which are the most interesting ones in our case. The model that we test with, it is the SMT Next. From previous experiments we did, it is the best model that performed on all the data sets. So this model, what it does is that the feature extraction process, it is replaced with a ComNext, and it was the best implementation. And we keep only the first three stages to do not perform a heavy reduction of the image for the feature map. We have 8 transformer layers, and the embedding size of the features, it is 256. You can see more details in the implementation we have publicly available. So our baseline approach is that since we do not have an end-to-end model to test this against, we decided to use a commercial tool for comparing our results, which would be like the thing that users would use to perform transcription if they do not have access to those systems. So we use the Photoscore tool because it is the one that is mostly cited in OMR research. So we considered it was the most interesting to use. So what we do is to convert the images to the TIFF format, which is the one that Photoscore uses. We perform transcription with Photoscore Ultimate 6, and we obtain a music XML file. We then standardize them through the MuseScore tool because converter tools prefer to use, in this case, we use Music 21 to perform conversion, prefer to use MuseScore XML format rather than raw music XML format. And then we convert it to Hammer Kern straightforward with the same tool with Music 21 and then perform comparison. So one thing is that we considered in our research is that photo scores cannot be fine-tuned to end-to-end Pianoform transcription. So comparing it directly to a full fine-tuned model, it is rather unfair. So we propose two model versions. First, the SMT, which is the model trained solely on synthetic data to get a similar scenario. And then the SMT-F, which is one which is fine-tuned to the target data sets. Just to be clear, what we are doing is suppressing the last fine-tuning step to get the SMT version with only trained with synthetic data. So the results are the following. First, we see that the seed music transformer, it is an architecture capable of learning and transcribing full page scores. The fine-tuned version gets the best results, obviously, with an average 8% of symbol error rate in the Mozarteum dataset and a 15% error rate in the digital police scores dataset. Also, we observe that the model without fine-tuning, just trained on synthetic data, it performs better than the Photoscores tool. So which is good news because even of not having the data, you get better results than the commercial OMR software, which is a clear advantage. Although we see that in the Mozarteum, the difference is bigger because the synthetic data is more close to the real data. And in the digital police scores, the difference is not so big because we have some gaps between synthetic data and real data. And that gap is seen also between the fine-tuned and non-fine-tuned models. We observe that indeed fine-tuning gets the huge amount of performance. And we believe this is because not only of the language differences, but also on the image differences. So we see here that there is room for improvement, specifically in synthetic generation. Also, we have some qualitative results. This was spoiled by David, but well, I allowed him to show the images. So for this input image, this is the transcription of photo scores. As you can see, it is very messy because it avoids a lot of errors, it invents other ones, and it gets a lot of errors indeed. By the way, this was rendered and shown with the Music Diff tool, which was discussed previously. This is the result of the seed music transformer without fine-tuning, just on synthetic data. As you can see, it has some problems on the reading of the last systems. It doesn't say any symbols at all. And also there are missing connections and slurs because it is not on the synthetic vocabulary, sadly. And this is the result of the seed music transformer fine-tuned. As you can see that we get the best option of it. Also, just as a reminder, the weights can be visualized, and you can see that the model can perform reading order. This is from an old example because I didn't have time to make a demo from the real data. And well, to wrap up things, the seed music transformer is presented as an end-to-end full-page transcription system, which is a sequence-to-sequence model trained with synthetic and curriculum learning, that it is compared with commercial software and gets very good results, especially when the model is fine-tuned into real data. But also, it is interesting the fact that it performs this baseline even at zeros of transcription without seeing any of the real data or the text data in this case. So we think that it is very good news to have this model and also that it shows these capabilities. Of course, there is room for improvement in future research. There is room for improvement specifically in the performance in zeros of transcription, just getting better synthetic data, more variability, also pre-training language, etc. And also there are other works that may be interesting in this model. For example, since attention mechanism can be seen, maybe we can profit the attention matrix to other practical tasks, which is something we are working with and it's going to come soon, I expect. and also to expand its capabilities for music document information extraction, which is something that I will talk in the next presentation. Well, for the moment, I hope you were interested. The source code is available. It is open source. And also, you can find the model weights, download them, and work with that through the Hugging Face Transformers API. I hope this presentation, although it started a little bit chunky, was interesting to you. Thank you.
Thank you, Antonio. Thank you very much. You went over time for 5 minutes, so I'm going to take it away from your next paper.
Okay, I will run.
You'll pay back. Does anyone have any questions to start with? Yeah, Felipe, please.
Yeah, it's me.
Yeah,
okay. So thanks for the presentation. It's very interesting. I have a couple of questions. The first one is related to the the results that you obtain in terms of internal structure, music structure in the documents that you obtain. Is there, for instance, an attempt to decompose with voices and to obtain something which is as fine-tuned as what you could obtain with a manual transcription, if you want to have a very fine description of the parts of the piano music, for instance?
So just to be clear on the question, it is that if the model is able to get information about the document itself, like a structural document, or
well, if you encode a score, you probably want to encode voices in order to be more reliable about how you represent your music. So my question is whether the system does the same kind of work, or if it's just outputs crops of notes that are okay for the display, but internally, which are blurred, the distinction between voices is blurred.
Well, actually, the hand-on-kern notation system does a lot of work on that because its encoding and the way it represents music, it implicitly encodes information about the voices and the voice splitting, and also in which moment the voices are divided and joined and such things. The model, it is not trained explicitly, or the data sets are not annotated in that way. So the model, let's say, for the moment, although it's something that we're still working on, only outputs the hand-on-kern document of the full page score. It doesn't get more information that hand-on-kern is not able to relate. Just for the record, for example, voice splitting, this is something that the language covers and can be identified in the structure of the document. But and specific annotations or specific symbols or dynamics and such things are something that's still working in progress. It's something that's not covered yet.
Thank you. Any other question? Jan, please.
So if you would compare the system not to PhotoScore, but to a system with like an oracle giving it the layout analysis and then looking at the best system you have for single staff Pianoform transcription, do you have this drop in do you see any drop in performance resulting from this curriculum learning part, and like how much of the final error does it account for?
You mean in transcription quality? Like
yeah, like how many of the errors are the result of going from single staff to full page recognition?
So, well, actually, if this is not something that we have evaluated, because the curriculum learning just takes care of that. But if you fine-tune directly in the data set from a single system, for example, if you pre-train a single system model and then you fine-tune without the curriculum learning, just learning the reading order of the full pages, it heavily depends on the quantity of data you have for that. However, we have seen, or when we perform these comparisons in some ablation studies, we observe that both steps are really important, but the most important one is just to read that single system stage, that first reading order. The other one can be somehow learned with few samples. So the performance drop, it is not that heavy if you already have a system that knows how to read
But
music systems.
Antonio, I think Jan is not asking about the training. I think he's asking about the final performance, right, Jan? Like,
Well, kind of. I mean,
you do first layout analysis and then system-wide recognition, or you go full end-to-end. How much error you add because of this higher complexity of the problem?
Actually, it shouldn't that much because well, the thing is that we haven't tested that yet. So this is something that has to be explored because we do not have layout analysis systems for Pianoform scores. But it shouldn't add that much of an error because, of course, when parsing the field document, you are having in context everything. And one thing that we should bear in mind is that the layout analysis systems do not take care, or when transcribing individually music scores with that, do not take care of the cross-staff interactions that are between the full page. So in this case, I cannot give an exact answer because it is something that we haven't tested, so I don't have evidence on that. But I would expect that the performance drop, it is not that heavy. It can be just assumable.
Sorry, Bertrand, can you put the question in the chat and we'll discuss it at the end of the session since we're running out of time? Sorry, thank you very much.